Welcome to the 2014 Fall Refresher Weather Training Module. Our subjects this fall include icing and turbulence. And at the conclusion of this module, you should be able to identify the characteristics and effects of icing and turbulence that impact aviation. So let's get started. What is icing? Icing, in general, is any deposit of ice forming on an object. Its occurrence on aircraft depends on two main variables: temperature, and the presence of visible liquid moisture in the form of supercooled water. Supercooled water refers to water droplets that exist below freezing. Ice crystals, such as you find in cirrus, do not cause aircraft icing. This is an important topic for discussion with Minneapolis controllers because of our area's proximity to frequent icing conditions. Here's a map that shows the geographic frequency of icing conditions across North America. The Great Lakes create a maritime influence. The lakes provide increased moisture under cold conditions, which can lead to an increased frequency of aircraft icing. So where do we find supercooled water? Freezing is a complex process. Pure water, that is, water that has no impurities whatsoever suspended in the air, does not freeze until it reaches a temperature of nearly minus 40 degrees Celsius. So supercooling is more likely with smaller and purer water droplets. Typically, liquid water exists at temperatures between 0 and minus 10. Between minus 10 and minus 20, liquid droplets coexist with ice crystals. And below minus 20, clouds are generally composed entirely of ice crystals. But strong vertical currents, such as you find in a cumulonimbus cloud or a thunderstorm, may carry supercooled water to great heights where temperatures are as low as minus 40. So what are the different types of icing? Well, we're referring to structural icing, that is, ice that sticks to the outside of an airplane. This forms when supercooled water strikes the aircraft, and it can accumulate on every exposed surface. It's categorized into three types: rime, clear, and mixed. Rime ice forms from smaller droplets with lower liquid water content. It's mostly found in non-precipitating clouds. It's the most common but least serious type of icing. It's typically well controlled by de-icing equipment. It might change the shape of the airfoil slightly, but its brittleness makes it easier to remove. Clear ice, on the other hand, forms from larger droplets. Usually this involves clouds with higher liquid content or precipitation. It's more hazardous than rime because a pilot actually may not see it. It has a smooth, clear appearance. It's heavier than rime ice, it can be difficult to remove, and it can spread beyond the reach of de-icing or anti-icing equipment. Mixed ice appears as layers of relatively clear and opaque ice when examined from the side. It combines the effects of both clear and rime ice. It can radically change the shape of the airfoil and add significant weight to the aircraft. When crews report icing conditions, frequently it's in reference to how well any de-icing equipment on board is handling the accumulation of ice. Here are the four categories of intensity of aircraft icing. With trace icing, usually the de-icing anti-icing equipment is not being utilized unless the icing is being encountered for an extended period of time. Under light icing events, usually it's just occasional use of de-icing equipment that removes and prevents any accumulation. But with moderate types of icing, the use of de-icing and anti-icing equipment is continual, and flight diversion then becomes mandatory. With severe, the rate of accumulation is such that the de-icing anti-icing equipment fails to reduce or control the hazard. So what controls the severity of icing? The severity of icing can be dependent upon aircraft type and design, the time in contact with supercooled water, which is influenced by airspeed and flight altitude, and of course meteorological factors, such as the supercooled water content, the temperature, and the droplet size. But it's important to note that the intensity encountered can often be determined as much by aircraft operation as by the present weather. Commercial jets are less vulnerable because they carry powerful anti-icing and de-icing equipment. They tend to cruise at higher altitudes where the temperatures are typically too cold for icing. It's mostly an issue for jet aircraft on climb and descent, and this is usually for aircraft without working de-icing equipment, or where you have moderate or heavy freezing rain. This can cause severe ice, even for jet aircraft. There are some unique cases for jet aircraft as well, something called engine icing or induction icing. This is icing that can occur at temperatures up to plus 10 degrees or 50 degrees Fahrenheit. The cooling occurs around the engine intakes due to the rapid loss of pressure. Or you could have various equipment failures on jet aircraft which may require not flying into any known or forecast icing conditions, and that may include environmental temperatures up to plus 10 degrees Celsius. Light turboprops are more susceptible to icing because they typically fly at lower altitudes, where temperatures often support icing. They also have less reserve power, they fly at lower speeds, they have less de-icing capability, sometimes no de-icing capability whatsoever, so the majority of icing-related accidents occur with non-jet aircraft. Icing is just plain bad news. It can increase drag while decreasing the ability of the airfoil to create lift. It can also increase the weight of the aircraft. This may result in stalls and, for certain aircraft types, lower angles of attack than normal. The aircraft can roll or pitch uncontrollably, and recovery might be impossible. The effect of ice can also affect an aircraft's operation in other ways. Ice may block fuel vents, block airflow into a pitot tube to cause false airspeed readings, accumulate on the carburetor, jam control surfaces, and, of course, ice up windshields. To escape icing, the general aviation pilot can exit the area of visible moisture, or ascend and descend to positive temperature. The jet pilot also has another alternative, that is, to ascend to altitudes where temperatures are too cold to support supercooled droplets. Now let's talk about turbulence. What is turbulence? Turbulence is the irregular motion of an aircraft in flight, especially when characterized by rapid up and down motion, caused by a rapid variation of atmospheric wind velocities. It ranges from annoying bumpiness, such as chop, to severe jolts which may cause structural damage and or injuries. The changes in wind over small distances required to produce aircraft turbulence can be created by a variety of phenomena, which can make forecasting turbulence a challenge. There are three basic causes of turbulence. There is convective turbulence, which is due to updrafts and downdrafts caused by convection, such as with thunderstorm activity. There's also mechanical turbulence, which is due to physical obstructions to wind flow. And there is wind shear. Wind shear is the abrupt change to wind speed with altitude. It's important for controllers to realize that these types of turbulence can occur at any altitude. In the convective case, you can get turbulence inside, above, below, and downwind of thunderstorms. In the obstruction case, you can have something called mountain wave activity. And with wind shear aloft, you can encounter turbulence inside flight-level jet streams. We call turbulence that is not related to convection or thunderstorms clear air turbulence, or CAT for short, although it doesn't have to occur in clear air, and clues to the presence of CAT can be seen sometimes in existing cloud patterns, which we will see later. Non-convective turbulence, known as CAT in winter, is mostly related to wind shear aloft or mountain wave activity. What are mountain waves? A mountain wave is an atmospheric wave disturbance formed when stable airflow passes over a mountain or mountain barrier. These waves develop above and downwind of mountains. The waves remain stationary while the wind blows through them. The significant effects to aviation are felt generally within 200 nautical miles downwind of the mountain range, and the mountain waves may frequently produce severe to extreme turbulence. Mountain wave clouds form on the rising branches of mountain waves and occupy the crests of the waves. The most distinctive are the sharp-edged lens or almond-shaped lenticular clouds, but a variety of stratocumulus, altocumulus, and cirrocumulus forms can appear. One thing that is helpful for aviators to note about this turbulence is that mountain wave turbulence zones set up in the same place when favorable conditions exist. This makes deviation routes through wave areas practical. Sometimes these are used by airlines. Denver Center deals with these routes frequently. Last spring, we discussed the hazard of wind shear close to the ground, but abrupt changes in wind velocity can occur at any level in the atmosphere. Two adjacent wind currents at different velocities can generate turbulence. And there are two cases where this occurs that are of special interest to aviation: in low-level temperature inversions or in upper-level fronts and shear layers. What is a temperature inversion? Well, an inversion is a layer in which temperature increases with altitude. Inversions occur within the first few thousand feet above the ground due to nighttime radiational cooling. They can also occur along frontal zones or above cold air trapped in a valley. Strong wind shears may occur across temperature inversion layers, which in turn will generate turbulence, especially for general aviation. In a jet stream, the location and intensity of turbulence is directly related to vertical wind shear. This intensity is maximized during winter when jet streams are strongest. Wind shear and clear air turbulence also increase around sharply curved jet streams associated with rapidly intensifying pressure systems. The resulting turbulence is usually confined to relatively thin transient layers. Flight planning around CAT through routing may be practical for long-haul and international flights, but it's best avoided by short-haul flights through altitude selection. Here is a weather map showing a tight pressure gradient in the upper atmosphere overlaying a surface front. If a strong jet, say with winds of 100 knots or more, is immediately adjacent to an area of much lighter winds, say 50 knots or less, the horizontal shear or change in wind velocity over distance is a clue to strong vertical wind shear, which is related to flight level turbulence. The area of worst turbulence is most likely in the zone of transition between high and low winds, which for a west to east jet stream is on the cold or poleward side of a jet. Let's take this example and turn it on its side so you can see a vertical cross-section of the jet stream. The jet core is shown in the top middle. There is a zone of transition between warm and cold air masses, which is known as the upper front. The upper front is simply the upper or higher portion of a surface front. It is in the upper front where you find the most significant wind shear and potential turbulence with a jet stream. For jet pilots, knowing the location of the tropopause and the stratosphere in this case can be helpful. The tropopause is the boundary between the troposphere, the lowest layer of atmosphere, and the next layer up, the stratosphere. Jet pilots are trained to reduce speed when encountering CAT, and that's because most jet aircraft have min-max turbulence penetration speeds. But also flying into the stratosphere may avoid clear turbulence. The more stable and lower wind velocities are in the stratosphere. A rule of thumb is to get above the tropopause level by 3,000 feet or more. Flying at the tropopause level can actually increase turbulence. Another alternative is to drop altitude and get below the base of the high wind shear. Also in pre-flight, routing on the south side of a jet core, where you find strong tailwinds, is preferable also for avoiding turbulence. The height of the tropopause can vary considerably day to day over a given location. Its height may be anywhere from around 25,000 feet to over 45,000 feet, but it generally averages lower heights in the mid-latitudes in winter. It's those lower tropopause heights that can make flying into the stratosphere become more practical for large aircraft. The presence of strong shear produces overturning motion, which results in vertical circulations known as eddies. When these are of the right size, they can create significant turbulent jolts to aircraft. With enough moisture, sometimes visual clues in the clouds, either as wave shapes or linear bands, indicate the presence of these vertical circulations. These linear patterns can frequently be seen in satellite pictures, perpendicular to the wind flow. They are indicators of the presence of turbulence in some layer. They are known as transverse bands. These herringbone patterns can also be seen in relation to mountain wave activity. Here's a picture over Colorado and New Mexico, with wave clouds being produced downwind of the mountains. Transverse bands can also appear as scallops on the edge of cirrus shields. The airflow around a cyclonic storm is superimposed by the red arrows in this picture. The shears produced by this pattern are creating the bumpy pattern on the edge of the cirrus, here as shown by the yellow area. Under turbulent conditions, crews may report a variety of ride encounters. You might get light turbulence reports in locations right next to moderate ones. What is going on? Well, the turbulence severity can vary with aircraft size, that is, larger is less bumpy. It can vary with aircraft airspeed, slower is generally less bumpy. It can vary with the attitude of the aircraft and the wing loading of the aircraft. So typically a range of intensities reported in the same area at the same time is not uncommon. Turbulence reports are also very subjective. Pilots still have to estimate how bad the turbulence is based on what they are feeling or seeing in the cockpit. This often can be less intense than the ride passengers experience in the cabin. Injuries are frequently reported with only moderate turbulence. It's also important to note that CHOP, strictly defined, is rapid and rhythmic bumpiness without noticeable changes in altitude or attitude. It usually does not denote hazardous turbulence, but the word CHOP may be incorrectly used at times to describe the actual ride, such as in severe CHOP. Finally, let's look at a case where a jet stream recently caused significant turbulence in the Minneapolis region, and the role pilot reports played in communicating this turbulence. At 12Z on the 21st of December in 2013, there was a strong jet cutting through the Minneapolis region from Kansas through Michigan. Inside the red circle, you can see a huge change in the wind speeds at 30,000 feet, from Colorado and South Dakota going east into Kansas, Nebraska, and Minnesota. By 0Z, the reported winds on the jet had intensified, and the wind shear, going west to east, was still there. These were the reports available that contained severe turbulence, mostly passed on by Minneapolis air traffic controllers, that Delta Airlines had received in their operational control center. This is an actual turbulence display that Delta Airlines uses, which plots pilot reports as they come in, mostly through the weather wire originating from air traffic control. Based on the reports from the Minneapolis Control Center, they had issued an in-house advisory to their dispatchers and crews to avoid the severe altitudes over the Nebraska region. The reports started with one severe pilot report around 1611 Zulu. By 1643 Zulu, Delta had the advisory out. By afternoon, the volume of severe reports had decreased. They lowered the expected intensity in another advisory. This now allowed Delta crews and dispatchers more flexibility on where to flight plan. We asked Delta to provide some feedback on this incident. This is the perspective of Delta meteorologists and operational staff on the event. Timely PIREPs helped us inform many flights, to the intensity and area of worst turbulence. Initially, bad rides caused 3 crews to try to find smoother air lower, where they actually descended into worse turbulence. But eventually, communication of ride reports, both turbulent and smooth, was made by air traffic control that later assisted Delta in advising and routing flights. It's important to stress that turbulence costs airlines money and injuries, lawsuits, and time aircraft are out of service, not to mention thorough cleaning. So even though some of their flights encountered turbulence, they were successfully able to keep many of their flights out of the most severe activity. Having those pilot reports during an event like this helped them significantly. It's important to realize that the aviation community depends on frequent, accurate pilot report information. This concludes the Fall 2014 Weather Refresher. Thanks for your attention, and thanks for keeping the skies safe.